Hello, welcome to today's class. So today we'll be looking at memory organization, one part of microcontroller or the 8051 microcontroller. So we'll be looking at how the internal memory of the 8051 microcontroller is organized. So head straight up to what we have for today. So first of all, we'll be looking at memory, literally or basically what a memory is. I think from our previous classes, we have looked at what a memory is, and say it's a component or system used to store data and instructions, either temporarily or um, permanently, depending on the kind of memory that is used. So literally we have two categories of memory. We have the primary and the secondary memory. The secondary memory is made up of external memory, which are the um, hard disk, the solid state disk, and the others. While for the primary memory, which is what the our systems primarily use, so we have the RAM and the ROM as well too. And for the RAM, we have the different types of RAM, the SRAM and the DRAM, while we also have the PROM, the EPROM, and the EEPROM. And so if we go back to our class on memory, we'll be able to can see what these memories are. Yeah, these are what we have here. So we'll go straight up to we'll have the memory organization itself, and literally for the 8051 microcontroller, it's made up of a 16-bit controller, which comprises of 64 kilobytes of program memory. This program memory it's literally the ROM, which I use to permanently store data and information. So the 8051 microcontroller memory is divided into the program memory, which is the ROM, and the data memory, which is the RAM. We know that instructions are stored in the RAM temporarily because instructions can be overwritten and it can be reused afterwards. And we also have the external memory. So for the program memory and the data memory, we have the internal ROM and the external ROM. We also have the internal RAM and the external RAM. I mentioned it before. For depending on the kind of operation that is being carried out, and so we can be able to use either the internal RAM or the internal ROM, depending on the size of the operation we are to carry out or we are to use. We'll look at the internal ROM. Basically, the internal ROM, I would say, is a non-volatile memory that is used to store the microcontroller program permanently. While for the external ROM, basically the internal ROM is made up of 4 kilobytes. The size of the internal ROM is 4 kilobytes, and the addressing is used from the 0000H to 0000 for F0FFFH. So if we count from 0 to F, we'll be able to get the 4 kilobytes of memories. Then you said depending on the requirements, an external memory can be used, which is an additional 60 kilobyte. So which is addressed from 1000 to FFFFH in size. We can actually see that in the next figure. We have looked at the internal RAM and external internal RAM and external RAM. And we said the internal RAM is made up of 4 kilobytes, while the external RAM is made up of 60 kilobytes, so a total of 64 kilobytes. So this is an illustration of the internal RAM and the external RAM. So in a situation, we have different cases or three cases of using the ROM or the program memory. We have the case one, which is 4 kilobytes of internal ROM only. So if we are using just the 4 kilobytes of internal ROM only, it's just the way it is. Then the second case is the 4 kilobytes of internal ROM plus 60 kilobytes of an external ROM. So this is illustrated in figure 1. So what this means is if we are doing that, then our EA pin will be connected to this, is which will be giving the logic 1. While the third case is 64 kilobytes. So the total of this will give us 64 kilobytes of program memory. While we also have, if we only use just the external ROM of 64 kilobytes, it means that the EA pin will be given a logic 0, which is connected to ground. Yeah. So this is also, if you combine these two together, we'll have the 60 kilobytes of external and 4 kilobytes of internal together will give us 64. So the next is the data memory, which is also called as the RAM. So it literally stores program temporarily while execution is going on. So the internal RAM of the microcontroller is made up of 128 bytes, which is an 8-bit data address bus, while the external RAM of a data memory is made up of 64 kilobytes, which is a total of 16 bits of address bus. So this is the structure of it. So you have the internal and the external. So in most cases, we will tend to use both the external RAM as well. So because it's 16 bits, and our microcontroller is a 54 microcontroller is a 16 bits microcontroller. We'll have the internal RAM and the external RAM. Like I said, the internal RAM can be moved up to 256 if we want to use a 16-bit internal RAM as well. So that's then, while the external RAM. So if you want to use the external RAM, you give the instruction. We'll have the instruction what we call the data pointer register. So the data pointer register is used to access the external RAM indirectly. So this is the instruction I will use if we want to access the external RAM. Now the memory organization is divided into three parts. We have the register banks, the bit addressable memory or bitwise addressing, and the general purpose memory. So we'll look at them individually. And this is the organization of the memory. We'll have 32 bytes of register banks. We have 16 bytes of the bit addressable memory, and we'll have 80 bytes of general purpose memory. So if you have add all of this together, we should be having is it a total of 128 bytes. So let's move on to discussing them individually. So the register banks, of course, you said is used to store information temporarily and is divided into 4 different banks, which is bank 0 to bank 0, bank 1, bank 2, bank 3. And these banks, they are used, remember in your PSW, you said there are 2 bits in our PSW, which is bit 3 and bit 4. So in our PSW, we have bits 3 and bit 4. They are being used to select these register banks, and we said Each of these register bank, which is bank, let's take for instance bank zero. Bank zero have eight different address. So we said 8054 is has four register banks, with each bank having eight arrow registers which are used for many years. So each of these bank have different registers, which is register 0 to register 1. Sorry, register 0 to register 7. And this is just an example if you want to select, or if you want to um, make use of the register bank. We'll see that in most of the instructions, it's we are using the R0 or R1 or R2 and all that. So those identify or uh, um, um, shows that we are using the register banks, or the memory of the register banks. To have the first instruction, move R0 H0C. So we have to move the value 0ch into register R0. We also have move A R0. So it means that we have to move the contents in register R0 into our accumulator, and so on. So you look at the instruction and it gives that. So this is just a structure of the register bank. Said the each bank have different eight arrow registers. That's what that implies. And the classification, like I said, it uses the bit 3 and bit 4 of our PSW. So we have PSW 3, PSW 4. So we could give an example where we said set B PSW 3. So what that means is we have to set, or we have to select PS. So if we have PSW, normally the two are being set as 0. Or so what it means that we are selecting bank 0. Now, if we said set B, or if we want to select bank 1, we can now give the instruction set B PSW 3. So it means that PSW 3 will be given the logic 1, while PSW 4 will be given the logic 0. So if we do that, this is what we are going to get, and we'll be selecting bank 1. The same thing applies if we want to select for bank 2 and bank 3. So for bank 2, we have to set PSW 4 and all that, so on. So, and each of these banks have a different memory location from 0 to 07, 08 to 0F, 1 to 17, 18 to 1F. So each of these is 8 bits. Now the next one is the bit addressable memory. Now this bit addressable memory helps if you want to select individual bits in a particular byte. So you know in a particular byte we have um 8 bits. So if you want to select an individual bit in in a particular byte, then we can use the bit addressable memory. So said it's a type of memory organization that allows programmers to access individual bits of memory locations rather than the um, entire byte itself. So that's what we do that. So it's also called bitwise addressing. So if you want to do just a bitwise addressing, you can use this bit addressing memory. You can also do a bytewise addressing too. So as we go on, we actually see that. So this is just an illustration of how the bitwise addressable memory works. So if you consider, let's say we consider an estate that has 16 blocks of houses, or 16, not 16 flats. We have 16 blocks of flats. So that 16 blocks here is given as 16 lanes, and each of those lanes or each of those blocks are named as 20H, 21H down to 2FH. Now say each of these blocks or each row consists of 8 houses, which is eight flats, and we address each of those 8 flats as 0H down to 7F. So if we do a total of from 00H to 7F, we'll have a total of 128 flats or 128 houses. So it means that if you consider block 20H, so we'll be having for 8 flats, we'll be having 0H down to 07H. That will give us for flat 20. So you do that and it goes on for that. And these are the instructions if you want to now select a bit. So if you consider the first instruction, clear 0F. So what clear 0F means is that if you go back to this diagram, so which bit is 0F? Oh, I'm sorry, 0F here. Which bit is 0F? Or we and what where which of the memory location is 0F located? So if we look at this, we'll see that memory 0F is on the memory location 21H. And what is the position of this 0F? We'll see that the position of this 0F is at D7. So this D0, D1 to D7, they are represented as individual bits in this in each of the address memory location. So we said that we have to set this bit 7 of the memory location 21H as 1. So we are setting it as 1. That is what this is. So we are clearing it, which is making it 0. That is what this instruction means. The same thing applies for the second instruction. We are now to set, so we have to make this 4H. So if you look at 4H, 4H should be somewhere around this location here. So we have to make 4H as 1. So we are giving that logic once. And what it means is that 4H or 42H is the third bit, which is D2 of the memory location or the RAM location to 28H. That's what this instruction says. So if you can do that, if you expand this, then we should be able to get these other two instructions. Now we can also do a byte-wise instruction. This here gives us a byte-wise instruction. So what it means is move 20H, comma hash FFH. This FFH means giving a logic 1 all through. So what it means is that 20H, this is 20H, this is memory location 20H. All of the bits in this memory location 20H give it the logic 1. That is what this instruction is telling us to do. Give all the bits in memory location 20H as 1. That is how the bitwise memory or bitwise addressing operates. The general purpose, like I said, it's being used by programmers to directly or indirectly use the memory addressing or memory locations, and it's taken from 30H to 7F. So if you add all of them together, we'll be able to get a total of 128 bytes. And this is also called like a scratch pad. So it's more or less like you're playing around with different memory locations and all that. So and these are just instructions that can be used for general purpose memory. So these are the various or different instructions that can be used, not just limited to this, but generally this is just some examples of direct and indirect addressing which can be used for a general purpose memory set of registers. So depending on the specification, you can use the direct or indirect addressing mode for the general purpose registers, yeah, or general purpose memory. So the next is stack pointer. So basically, the stack pointers, they are used to temporarily store or hold some variables or values, and literally these variables are more, when you're considering memory, these variables are more of an address or a location, or a memory address of an instruction or wherever it's being stored. That's what the stack pointer is being used, and the stack pointer is more of, it's a register on its own, and it's used to select or remind the system, or the sets of instructions that are being stored for usage. So literally, you have a stack of instructions being um, being to be executed. Now, for you to actually pick out or take up any of those instructions from the stack, from the stack register, you use the stack pointer register to actually do that. So for the example, you have the move SP. So SP is more of the stack pointer register, which is, it means that it's initialized to 0. Then the other two commands that are being used to in the stack pointer are the push and pop. So basically, the push is more of your adding an instruction into the stack. You're adding a set of instruction into the memory stack. So that's what, when you use a push instruction, or if you want to use the pop instruction is you're extracting. So we say for the push, they say push accumulator. So it means the stack pointer incremented by one first, and then the content of the accumulator is stored in that stack location, which is stored in the stack pointer register. While the pop, we say the data is retrieved from the location of the stack pointer into the accumulator, and then the stack pointer is decremented by one. So it's more, you have a rack of information. So if you pick out an information from there, it reduces. If you add an information to that rack, it increases. So that's what the stack pointer is usually used for. So we say, well, it's just to remind the system. So especially when you're dealing with interrupts, especially when we have looked at interrupts, especially when you're dealing with interrupts, that's when you use the stack pointer more, because you have sets of instructions being used so that you don't forget what you're doing. So if there's an interrupt in the system, with that stack pointer register, you have those instructions there. The system performs the executes what the interrupt is doing, and then later comes back to execute the set of instructions that are in the stack pointer register. So basically, these are the different memory organization areas. So I looked at the different types, which is the register banks, the bit addressing, and general purpose. We also looked at the sizes of the data memory and the program memory, as well as different types of memory. Yeah. So thank you.